Okay, hello everyone. So this is a video I'm making for our HEC HMS number 2 lab. Okay, so let's begin. So here we have the homework that you'll be given to do, and we're going to go through this homework together in this video, okay? So it says calculation of rainfall distribution and discharge. So this is a table for a Ulsan station, and it shows it shows the name of the station here, and then from here to here is the frequency. So it's 2 years frequency, 3 years frequency, 5 years frequency, and so on. So it means how long it takes for rainfall to happen again within certain amount of years. So if we say 150 years frequency, it means it will take approximately 150 years for this same amount of rainfall to happen. So it's a very rare rainfall event, okay? Because this type of rainfall only happens every 150 years. So on the x-axis we have for the x, the row, we have the durations. So this is 10 minutes duration, 60 minutes, 120 minutes, and so on. And we have to convert the minutes into hours. So the problem says calculate the frequency-based rainfall using time distribution by the Huff third quartile method and plot the design hyetograph for 1 hour interval and 24 hours duration. Using the data 150 years frequency, so that's 24 hours is basically 1440 minutes duration. So minutes converted into hours is 24 hours. And then for this frequency and this duration, we have 398.3 millimeters. So if you look at the table here, we have the 150 years frequency, and if you go all the way to the right, where the duration is 1440 minutes, which is 24 hours, we have 398.3 millimeters. So we're going to use this 398.3 millimeters for calculation, so remember that. So first we'll make a 24-hour 1 hour interval hyetograph with 398.3 millimeters, picking third quartile 50% exceedance median. So when we're going to see tables of tables like this. So we'll make a 24-hour 1 hour interval hyetograph with 398.3 millimeters in rainfall, picking third quartile 50% exceedance. So step 1, choose the row from the third quartile table. Take the 50% row values at duration 0 to 100%. And so what this means is, if you look at this table, these tables are showing time distribution of Ulsan analyzed by Huff method. So in Huff method, if you remember, there's first quartile, second quartile, third quartile, and fourth quartile. And these quartiles basically explain the type of rainfall, okay, when it rises and when it falls. So we're going to use the third quartile. And then if you look at here, it says exceedance probability. So what exceedance probability means, the chance for this type of rainfall to happen for this amount of duration. Okay, so for this problem, we're just going to use 50%. So we're just going to assume that this type of rainfall could happen at like 50% of probability. And then for duration, we have from 0% to 100%. So instead of having like 1 hour we have like 50 millimeters, 2 hours we have 60 millimeters of rain, we have percentages instead of hours. That's what Huff method is. So from instead of going 0, 1, 2, 3 hours, we're having 0%, 10%, 20%, 30%, and so on. Okay, and then since we chose 50% exceedance probability, we're going to use these numbers right here. Okay, so if we go back, these numbers, that's where all these numbers came from. Okay, so we have the numbers from the third quartile table, 50% for Huff method, from the Huff method, and then we're going to map each hour to duration percent. So we need to have, since our question says 24-hour 1-hour interval hyetograph, this is what the question asks. So for 24 hours we have to convert them into percentages. Okay, so we're going to do 1 divided by 24 times 100 equals 4.17, and so on. Okay, so like this. So dimensionless time percentage is equal to elapsed time over total duration times 100. So we're basically converting the regular hours into percentages. And how do we do that? We basically divide each hour by 24 and times 100, because we're looking for 24 hours duration storm. Okay, so 1 divided by 24 times 100, you get this. 2 divided by 24 times 100, you get this. And that's how you get this dimensionless time in percentage. So once we have the dimensionless time in percentage, now we have to interpolate cumulative percentage at each hour. So the table gives values only every 10% of duration, so we have to linearly interpolate to the hourly x. So what this means is, if you go back to this table, the numbers are given only in like 10% increment. You see how there's only 10 intervals, and for each percentage you have a value that follows, right? So for 0% you have 0, 10% you have 2.5, 20% you have 6.4, but we have 0, 1, 2, 3, 4 percentages. So these values are not shown here, because this one goes from 0, 10, 20, not 0, 1, 2, 3, 4. Okay, so we have to interpolate. So we have to interpolate the cumulative percentage at each hour. Okay, so let's look at example A. So for hour 6, our homework problem, we have the 25% duration. So that means 6 out of 24 times 100 equals 25%. That's what it means. So 6 hours in 24 hours is equal to 25% percentage hours, or duration. Okay, so it's basically this, but for instead of 5, for 6, this is 25%. Okay, so we have 6 hour is 25%, but in our table we'll only have 0, 10, 20, and then 30. Okay, so we have to interpolate. See, 25% lies halfway between 20% and 30%, so we have to interpolate between 20 and 30 to get our value. So from the row, we have, when it's 20%, it's 6.4. And when it's 30%, it's 13.4. And you can find these numbers in the table, right? So when it's 20%, 6.4, 30%, 13.4. Okay? So yeah, 6.4, 13.4. So using these numbers, we can interpolate like. So using the numbers, we can interpolate like this, right, to get 9.9%. Right. So you know, you interpolate like you get. So you're basically trying to get the ratio by 13.4 minus 6.4, and since 25% lies halfway, it was multiplied by 0.5, and then 6.4 is added because 25 is 5 is after 20, so 6.4 plus all of this to get 9.9%. Okay. And then to convert to cumulative depth, now we use the 398.3 millimeters, which was given to us. And then we multiply this percentage to this, okay, to get the cumulative depth. So 398.3 times 0.099 equals 39.43 millimeters. And this is for our 6. And now to get the hourly depths, to draw a hydrograph like this, we subtract the whatever value from the previous value. Okay, so we have the so to get the hourly depth, so we already did all that. So we also need like R5 to get the hourly depth. Okay, so right now we have 39.4346, and for 5 we have 27.81, but these are not hourly depth. Okay, this is cumulative. So what so cumulative means all the numbers that came before whatever they may be, if there's some number here, some number here, some number here, some number here. So 27.81 is equal to all of these added. Okay, it's not hourly data, it's all of this data added to one value. So if we want to get hourly value for 6 hours, so 39.43 is also addition of all of these. Okay, so we have to subtract 27.8137 from this, so we can get hourly value for 6 hours. All right. And if you do that for all the time and hours, you get this table. Okay, so this is how you get rainfall distribution table from Huff method. Okay, when you have this type of tables given to you. Okay, so on our so what we did in our lab was you were given regression equation. So you were given regression equation in our I believe second lab, and also this was on our exam. So it was like an equation y equals something something x6 plus something something x fifth and something something, right? So this something in the front of every equation, it was probably in some decimal number. So in this case, you're supposed to use this number to calculate the Huff method, but in this homework problem we have these tables and with this percentage to use, okay, to solve the Huff method. So this is how we get the rainfall distribution table, and you're going to use this table. Okay, so this is the first data you have to use